As you said, yes, I'm a second year PhD student currently studying at UCL, and I've been primarily focused on researching bicycle sharing systems throughout my PhD. So in this presentation, if we flick over to the next slide, I'm just going to talk to you a little bit about the situation in which I found myself in at the start of my PhD, followed by some of the questions which I wanted to answer throughout my PhD, and then finally, I'll present to you some of the results. So if we start off with the situation, so if we move on to the next slide, bicycle sharing systems have seen a vast increase in popularity in cities all around the world, and there are currently estimated to be around 3,000 bicycle sharing systems in operation, with a current market value of around 6 billion euros. And conducting a brief literature review, we find that there is no comprehensive comparison of these bicycle sharing systems from around the world. There are a few comparisons which have been researched previously, but these are primarily regional or continental and don't span different continents. And so I was very privileged enough to be able to use the most comprehensive bicycle sharing system dataset, which is available to me. This was provided to me by Oliver O'Brien, who's a colleague of mine and works in the CDRC. And he's been collecting bicycle system data himself from individual operator websites since around 2010. And to date, he's amassed around 600 systems from around the world, primarily focusing on docked bicycle sharing systems. So those are the systems like the Santander bikes that we have in London. And these are from all around the world, so 57 countries, and amassed to around 1 terabyte. And using this data, Oliver, James Cheshire, and Michael Batty have previously done some research using this, creating a comparison of 38 bicycle sharing systems around the world. But this was conducted in 2014, and I wanted to create a more updated and comprehensive comparison. And so that was the main objective for this piece of research. So if we move on to some of the questions which I wanted to answer within this research, so the primary question was, what can we learn from the data? And so looking at the literature within around bicycle sharing systems, we find that a lot of the research looks to investigate the patterns and use within an individual system, how factors influence the use of bicycle sharing systems, what makes them efficient or successful. But there was a large gap, like I mentioned earlier, around the comparison of bicycle sharing systems around the world. And so the answer to all of this, as we move on, was to create a global comparison of bicycle sharing systems, which I will be presenting to you today. So the primary limitation within this research was the data. The data was limited to dock capacity data. So this can be collected from operator websites and APIs. And this information typically contains the number of bikes and the number of spaces within each docking station at a particular point in time. For the majority of the systems within our dataset, this has been collected at 2-minute intervals, so we can start to build up a detailed picture of the flows of bicycles in and out of these docking stations. And so using dock capacity data, it was manipulated in various different ways to be able to create metrics which we could be able to use to compare these bicycle sharing systems from around the world. So metrics such as the number of journeys, the number of bicycles, the number of trips per bike per day, the operational area, docking station density, daily journey patterns, just to name a few. I would like into a bit more detail about how this data was manipulated. So in the next slide, I'm just going to show you an example of how we have manipulated the dock capacity data to estimate the number of journeys within each system. And so here we have two observations from dock 12 within a within a bicycle sharing system, and this data is collected every 2 minutes. And so at 2:24 within this particular dock, we see that there are 3 bikes and 2 spaces. And then the next observation we see 2 minutes later, we find that there are only 2 bikes and 3 spaces. So within these 2 minutes, we know that a bike has left this docking station, and therefore we can infer that a journey has been started. And so by ordering all this, the dock capacity data chronologically, we're able to build up a picture of how these bicycle sharing systems are used, and we can aggregate these figures to the number of journeys per day. So in this example here, we can see how I have been able to estimate the number of journeys in blue compared to the journey count in red. It's not very visible, or hopefully it's visible for you guys, but the journey data in red is actually a measure from the origin destination flows of each journey within a bicycle sharing system. And although it's much more accurate, the data is very limited to particular bicycle sharing systems. And so there were only around 20, I believe, which we had journey data for. And so within our analysis, this was purely used as a validation tool. So in this example here, we can see that for London, we have a very close match. And overall, I believe there was around a 0 to 15% error rate on any particular journey estimation. And so if we move on, we can see that after creating various different metrics, we can see how each individual bicycle sharing system has evolved over time. And so again, following the example of London here, we can see how from 2010, when we have our first data point collected, till the present day, we can see how this system has evolved both in terms of its size, with the number of bikes along the x-axis, as well as its use and efficiency along the y-axis, measured by the trips per bike per day metric. And we can start to see some interesting patterns within individual systems. So we can see how in Q3 of 2012, we find the largest spike in the number of trips per bike per day, which we can attribute to the use within the London 2012 Olympics. And then since 2015, we can see a very clear seasonal pattern, with the summer months in Q3 exhibiting much higher numbers in terms of the trips per bike per day compared to those winter months in Q1. So although this helps us to build up a picture of individual systems, the aim was to try and create a comparison. So in this next slide, because we are able to calculate the same metrics for each of these bicycle sharing systems, by plotting them on the same graph, we're able to make some visual and descriptive comparisons between these bicycle sharing systems. So for example, we can see that in this period between 2016 and 2018, Paris has actually fallen in terms of the number of bikes, as well as the efficiency and the trips per bike per day, while other systems such as Rio de Janeiro, for example, have both increased in the number of bikes and the number of trips per bike per day. Now, although this is useful in creating and stimulating in the way that it's visual and it helps us to compare bicycle sharing systems, it's not very robust, and it relies on the reader to make comparisons. And so one of the ways in which I wanted to make this comparison more robust was to include alternative confounding variables within my analysis. And so turning over to the next slide, conducting the literature review, I found that there were many papers which looked at the various different factors that would influence the use of individual bicycle sharing systems. And because these were based on individual bicycle sharing systems, it was important to look at as many as possible to start to build up a picture of which were consistently had high influence on the influence of the use of these bicycle sharing systems. So this was distilled down to 4 main confounding variables. So how hilly an area is, the weather or climate within that area, the social makeup or population within those bicycle sharing systems, as well as the extent of cycling infrastructure within those bicycle sharing systems. And these metrics were calculated for each bicycle sharing system through the use of a global raster dataset, which would then be overlaid onto the polygons of each bicycle sharing system for which we had data. And this would enable us to calculate the variables for each bicycle sharing system homogeneically. So after those variables are calculated, this graph here represents a map of the distribution of the 322 bicycle sharing systems for which we have clean and complete data. So this is by far the most comprehensive and global comparison of bicycle sharing systems around the world, which include all of the major continents, especially including China, Europe, and North America. And so using these 322 bicycle sharing systems, I wanted to create a more comprehensive way to cluster these bicycle sharing systems. And the data was split between a time constant and time series dataset. And although I wanted to be able to cluster these simultaneously, there are established methods to do so. And so I ended up using a 2-stage clustering method. And so in the first stage of clustering on the static variables, the bicycle sharing system variables calculated that I mentioned a few slides ago, as well as the confounding variables, were aggregated for the period of April to September 2018. And they were clustered using a k-means clustering algorithm to help build up a picture of the different groups of bicycle sharing systems which had similar attributes, both in terms of the way that they are used, as well as the surrounding context through those confounding variables. Then within each of those k-means clusters, I clustered the typical use patterns throughout a typical weekday or weekend using a dynamic time morphing clustering method. So this is a shape-based clustering method and just enables us to see how systems within these clusters are used throughout a typical day. So the results in the next few slides will hopefully make this a little bit clearer. So if we turn to the next slide, so we have 5 main clusters based on the k-means clustering in the first stage. So cluster 1 has been named very large, high-use bicycle sharing systems. This is because of the fact that they are very large, with the average population within these bicycle sharing systems of around 4.3 million within the operational area. They have on average around 18,500 bikes, 68,500 journeys per weekday, and an average trips per bike per day of 4.6. And on the right-hand side, we can see a graphic of that DT cluster. So within this k-means cluster, we have one subcluster of the typical use patterns throughout the day. And as we can see, all of these 3 systems exhibit a typical 2 commuter peak pattern throughout the day, where we see one peak in the morning AM commute and one peak in the PM commute home. So this tells us that these bicycle sharing systems are typically used by commuters. In the next cluster, we have large bicycle sharing systems in major cities. So these bicycle sharing systems within this cluster include London, Barcelona, Paris, New York, Montreal. And on average, the population within these clusters include 1.8 million with 25,000 journeys. And again, they are efficient with around 4.7 trips per bike per day. Now, in the subclusters, we can see that although subcluster 2, for the majority of systems, exhibits that 2 commuter peak, we find that for subcluster 1, there's one large peak with some spikes in those morning periods as well, but it's a more gradual use throughout the day. And we typically associate this with more leisure use. So these systems, which are in subcluster 1, may be primarily or dominantly used by tourists or leisure users, as opposed to those in subcluster 2. Following that, cluster 3 is another small cluster containing 5 bicycle sharing systems. This is named medium bicycle sharing systems with extensive cycling infrastructure, and this is primarily because this cluster contains the largest average length of cycling infrastructure measure at 1,500 kilometers. Now, although literature states that this is usually associated with a high use within the system, we find that the trips per bike per day for this cluster is on average around 1.5 for a typical weekday. And again, on the right-hand side, we can see a typical two-peak commuter pattern with subcluster 2 exhibiting a small system, Stuttgart, which exhibits a more jumpy and spiky pattern. In cluster 4, we have small to medium efficient bicycle sharing systems. So these are cities such as Milan, Lyon, Valencia, Helsinki. There are 66 in total. The average population within this area is 350,000, with an average of 1,000 bikes, 4,500 journeys on a typical weekday, and a very high average of 4.9 trips per bike per day. And again, the first 2 subclusters within this cluster show that the majority of these systems are primarily used as a commuting vehicle, whereas for those systems in subcluster 3, these are typically used by more leisure and tourism users. And the final cluster we have is small to medium inefficient systems. This is the largest cluster by far, with 233 of the bicycle sharing systems included. This has an average population of around 111,280 bikes within these systems, and 360 journeys on average on a typical weekday. And these are classified as inefficient because each bike is typically only used once per day, with the trips per bike per day figure showing 1. And here we have the messiest sort of use clustering. So subcluster 3, you can sort of make out the typical 2 commuter peak. And then for cluster 1 and 4, we can see that these are more gradual use cases throughout the day. And then in subcluster 2, we find a much more erratic use. And these are probably the smallest systems which exhibit very little use and therefore show large spikes within their use, typical use patterns throughout the day. So to summarize all of this, I found that the largest systems are typically located in East Asia. Other large systems are located in major cities around the world, such as London and Paris. Although there is a strong correlation between the size and the number of journeys within the system, contrary to the literature, little correlation has been found between the number of journeys and the slope and the precipitation within these bicycle sharing systems. We also find that the larger the system, the smoother the journey patterns, and during weekday, we typically see the majority of systems exhibiting a 2 commuter peak, which is typical. And then for weekend patterns, we usually find 1 large peak throughout the day. So those are typically leisure and tourism use. So that will do it for me in terms of the presentation. I have a few extra slides if people want to see the comparison in more detail, but any questions? Thank you.
Wonderful. Thank you very much for that, James. I hope my driving was suitable. I think it came across okay.
That was perfect. Thank you very much. Yeah.
You're welcome. First question in from Josh Hill. when inferring user journeys from station data, how do you account for the operator rebalancing bikes in the system? So TfL relocating bikes from one station to another.
So the truth of it is you can't really detect or account for those things within the dock capacity data, unfortunately. So we have to assume that these are the same across all of the bicycle sharing systems for which we've collected data, which is unfortunately not true. And so those validation methods, which I didn't get to talk about because I think one of the animations didn't work, but when we did the journey estimations, we found that there were periods in which we found a lot of data noise. And so it was necessary to identify those periods of noise which would cause large overestimations in terms of the number of journeys. Now, there is a possibility that the algorithm which I used to detect these periods of noise would also be able to identify periods of redistribution which would look like noise, where operators would be taking bikes in and out of a dock very frequently. So that's the primary way that I've tried to account for it. But in addition to that, the validating with the journey data found that there were, across the board, there were very little differences in terms of my estimation and the journey counts that we were presented within the journey data.
Great, thanks. Another question from Stephen Clark. If you still have access to these data, what's been the impact of COVID-19? What schemes are more robust to this major disruption? So changes in the mix of commuters, utilities, or tourists, correlated with geolocated cases?
So unfortunately, I do not have access to the updated data. But Ollie, who collects the data, he's been doing some research and he's got a really good article on his blog that I would highly recommend you read on the impact of COVID on these bicycle sharing systems. And essentially what I think he found, if I remember correctly, was that there was generally more use, but more gradual use instead of that 2 commuter peak. So because the weather was nice throughout the lockdown period within London, so this is just London specifically, there were more use cases, but in a more gradual, leisure-based use case compared to the typical 2 commuter peak. But I would highly recommend that you go to Oliver's blog to read more about the effects of COVID on cycling.
Great, and I think Oliver is here, so by all means chuck the link to the blog in the chat for everyone. Okay, another question from Pry Ketten. What characterises the cities with mostly leisure or touristic use? So I think they're asking what are the ones that are not commuter use, and I think you mentioned that briefly, but could you expand a little bit on that?
I haven't looked at that specifically. So the way I conducted my analysis was to look at the characteristics of the big groups first, using the k-means clusters, and then individually look at the use. So that's where you see the leisure and tourism use within those individual clusters. I haven't actually looked at the characteristics of those leisure-based systems, but that would be very possible with the data. So if that's something you want to know, please email me and I will do that for you and get those average statistics.
Great, thank you. One more question, Anna Barassi. Can you comment on the two-step clustering scaling issue and the potential impacts on the daily patterns?
Yep. So I forgot to mention it, that's a very good question, but I actually normalized all the daily use patterns throughout the day around 0 so that there wouldn't be any issues with scaling and we would just be able to cluster using DTW based on the shape rather than the scale.
Great, wonderful.
Does that answer the question? Yeah.
Yeah, no, that's a great answer. Anna says thanks. Great. We'll wait a couple of minutes if anybody has any other questions. I will take this opportunity to pass on an official communication. So just to remind everyone that we do prizes. So the voting link will be sent around tomorrow, but please think about the prize for the best paper and the best short paper as well. So please do have a think about those of the sessions you've attended, and the link should go out tomorrow. Okay, we've not got any more questions coming in. We've got a couple of minutes. Are there any of your extra slides you think might be interesting to comment on? One of them, maybe?
I can change the slides. So on the left-hand side here, this is just more of a visual representation of the centers of the k-means clusters. So you can sort of see how each cluster has very distinct characteristics. So you can see, for example, population is a large contributing factor to the distribution of those clusters as well as area. And we see that, so one thing that I didn't show in the other results was the fact that I split the most of the bicycle sharing system metrics between weekdays and weekends because they exhibit very different patterns. So even in a system which exhibits typical commuter use throughout a weekday, we might find leisure use on the weekend. And so it was very important to include those nuances within the data, and within the clustering, sorry. So you can sort of see those here. The right-hand side was another example of those subclusters, but it's a mess. So refer back to the other ones that I've included in the primary slides. And I think the other slides are just the numbers, the raw numbers.